Okay, so today we're going to go over the two special functions that really show how useful the Laplace transform is in solving some specific types of differential equations when the functions involved are not nice functions. In particular, if the functions are not discontinuous, or maybe they're not even functions in the traditional sense. So there will be multiple parts of this lesson, so we're going to focus on the so-called step function and the delta, or the unit impulse function. So we're going to start with the step function, define it, and show what's good, what's good about it. Then we're going to have to deal with a specific formula, a specific Laplace transform formula that is necessary in the context of using the step function. And then we're going to move on to the impulse function, and then again finalize with examples that show how to solve differential equations involving both. But just to summarize, the main theory, the main goal in the end is just what we did last time, solving differential equations via Laplace transform, except this time involving these special functions. So the step function is designed to actually deal in an efficient way with discontinuous functions. Now you may wonder why you need that. Well, for example, let's say you have a model that describes an electrical circuit. And then along the way, as the process moves on time, you have some switches that turn on and off the current. Right on that moment, you will have some discontinuous processes, right? So for example, if I turn off the light bulb, or a certain circuit, the current will drop suddenly. Or if you turn it on, it will increase suddenly. No matter what you do, if you imagine these switches, by default you will have some discontinuous processes, some jump discontinuities. So the step function is defined in relation to a specific time t equals a. So the step function simply returns 1 when t reaches the time equal to a. So let's write it down, the definition. Actually, in fact, let me actually sketch the graph of the function and then define it. So this is the time axis, and the function essentially does nothing until t is equal to a. So in the time interval 0 and a, the function is 0. So it returns 0. And then as soon as the time clock hits the value a, the function returns 1. So this is 1 on the vertical axis. So there are various notations for this function. I'm going to use the one in the book that we use in this class. So the notation is step of t minus a, right? So this is really a notation, right? So think of it as a notation for the function itself, which simply states that the value of this function is 0 if t is between 0 and a, and then it's 1 if t is greater than or equal to a. So again, a function that does nothing, or in other words, returns 0 initially up until time t equals a, and then once the time reaches that time value, t equals a, the function returns 1, and it stays 1 forever. So I'm going to explain a little bit why it's defined this way, but the best way to understand it is to really make an analogy with the switch I mentioned before. Think of this function really like a switch which is turned off initially. So it's in the off position in the beginning. And then as soon as time is equal to a, so as soon as the chronometer or the clock reaches this value for the time, then the function is, or the switch is turned on. And it stays on forever. So again, off in the beginning, as soon as the clock rings t equals a, then it turns on and then returns value 1. Okay, furthermore, why is 1? Why does it return value 1? Why is it defined this way? This is for standardization purposes. You can make it to return whatever value you want if you multiply the function by a specific value. So for example, let's say after time is equal 3, I want the output of that function to be 10. You simply write 10 times step t minus 2. What did I say? I forgot what time I said. But say I want at time is equal 2, I want the function to return value 10. Then you simply multiply the step function by 10, because the step function always returns 1, and you can make it return whatever value you want by multiplying that value with the step function. So we're going to move on with more suggestive examples, but that's the main idea. With combinations of the step functions, we can actually describe in a very nice way pretty much any piecewise defined function that returns different values at different time intervals. All you got to do is to essentially play with these switches, and then as soon as the function changes its value, you introduce a step function at that appropriate time with the appropriate coefficient in order to make the function return the value you want. So it'll be much clearer once we go over some examples. But let's write down this main idea. So the main use of this step function is that we can represent any piecewise function as a combination, as a linear combination of step functions at time points where the function changes its value. So make sure you write down the main purpose, because it'll make more sense once you go back to this idea, once you see the example. So the main use of the step function is that we can represent any piecewise function as a linear combination of step functions time points where that function changes its value. So let's actually go over a quick example to illustrate this. So suppose I have a function that is equal to let's say 5 if t is between 0 and 2. Then it's minus 2 if t is between 2 and 3. And let's put another value. Let's say 1 if t is between 3 and, let's say, 7. And then finally, let's say I want it to be 9 if t is greater than or equal to 7. So you look at the domain and you want the function to return various values for various time intervals. And also notice that the function will be automatically discontinuous, because at the points on time where the function changes its values, the sighted limits will not be the same, obviously, right? Because these are different values. So how do you do this? How do you represent the function with a linear combination of step functions? So the main idea is to start with the first value of the function, 5. And pay attention here. Then you're going to write down as many step functions as the time points where the function changes its values. So how many times the function changes its value? So it's once, twice, 3 times. So you start with 5, and at time t equal 2, you have some changes in the value of the function. You need as many step functions at those points as the number of times the function changes. So what you do, you leave some room for the coefficients and introduce these step functions in a linear combination. So some coefficient times step t minus 2 plus some other coefficient times step t minus 3 plus some other coefficient times step t minus 7. Okay, so as many step function as the number of times the function changes its value. Now, what is the magical coefficient that will make it so that the function returns what you want, minus 2, 1, 9, and so on? So remember, up until t equals 2, these functions return 0, right? So they do nothing. As soon as t equals 2, this turns on and becomes 1. So at that moment, you wanted to kill the previous value, 5, and put the new value minus 2. As you move on, and when t equals 3, this becomes 1. You want, in this coefficient, to kill the previous value, put the new value in, and so on and so forth. So all you do in each parenthesis, so let's write it down here, in each parenthesis below, you undo the previous value and put the new one in. So you undo the previous value and put the new one in. So in this case, at times t equals 2, I want to cancel 5, so I'm going to put minus 5 and put the new value in, which is minus 2. So again, pause for a moment to make sure you understand this. Each parenthesis, at each time point where the function changes, you cancel the previous value, to use a nicer term, and put the new value in. Now the function is minus 2, as it should. When the time is equal to 3, you want to undo the previous value. So if it was minus 2, you want to add 2, put the new value in, which is 1. All right, and finally here, when times is equal to 7, you undo the previous value, which is minus 1, put the new value in, which is 9. So that's how you actually represent any piecewise function as a linear combination of step functions. So once you compute these coefficients, this will be 5 minus 7 step t minus 2 plus 3 step t minus 3 and then plus 8 step t minus 7. If it's not clear why that's useful yet, well, remember the goal eventually is to take the Laplace transform of this, and we have linearity property in the Laplace transform. So with this tool, all I have to do is to make or to compute a formula for the Laplace of the step function, and because you can write any piecewise function as a linear combination of step functions, then you can take the Laplace of a piecewise function very easily. All you got to do is to write this function like this, and then take its Laplace transform. So just to formalize this process, let's actually write another example. Let's put this one and this another one too. Suppose your function, let me put here unspecified values just to make it clear. So suppose the function is a if t is between 0 and 1. The function is b if t is between 1 and 3, let's say, and then the function is c if t is between 3 and 5, let's say. So how do you write it via step function? F of t equals the first value in, and then plus combination of step functions at each time point where the function changes its value, which in my case that's 1 and 3. So be careful here, because sometimes actually let's say t less than infinity here, because I want to define the function for the whole real axis, right? Usually the last one is like t greater than 3 and then on, right? I mean t doesn't have any right bound here, right? Because you want to define the function for the whole real axis, for the full positive timeline. So one thing that people sometimes make a mistake, they put step t minus 0, for example, or something like that. So you want the time values for the step functions to be the values of the time where the function changes. So there is a change at time equals 1, there is a change at time is equal 3. Okay, what are the coefficients? Each coefficient will undo the previous value and put the new value in. So minus a plus b will be the first coefficient. Here it will be minus b plus c. So that's the main idea for all of these types of problems when you write the function as a combination of step functions. And one thing to keep in mind, you don't have to have constant values for the function. These values can depend on t, but the principle remains the same. So let's actually look at an example from the notes. So for instance, what if your function is t, if t is between 0 and 2, t squared, if t is between 2 and 3, and let's say it's 5 if t is greater than 3. When you write this with a step function, the same idea works like before. You start with the first value, so let's write it here, which is t. Then at the first point the function changes, which is times t equals 2. You undo the previous value, that means you subtract t and put the new value in, plus t squared. Furthermore, now at times t equals 3, you undo the previous value, which is minus t squared, and put the new value in. So step t minus 3. And this is how you represent the function with the other step functions. Okay, so the next part of the lecture will focus on how you actually find the Laplace transform of the step function. Well, actually, I'm not going to go over the proof. That's given in the notes. I'm going to just write the formula for the Laplace of the step function, then go on some examples related to it. But it's very important to have the Laplace table in front of you, because we will need other formulas in the Laplace table. So in the interest of time, I'm not going to write all of those formulas here maybe. Just if I use it and it's not here on the board, just make sure you have it in front of you and pause to see it. So make sure you have the Laplace table in front of you, because I'm not going to write all the formulas in that table. So stay tuned for the second part.